Good afternoon, YouTubers. Today we're going to be studying this reaction. I got this reaction where 2 moles of A can react to form an equilibrium with B, but B eventually will form C. So the reaction looks more like shown here, except this 1/2 is not there. I mean, this 1/2 you will see where that come from in a second, but the original reaction is this 2A coming or becoming part of B, but B can go back again to form A. So there's an equilibrium here, but then from B it will eventually form C. So the question is how we write the kinetics for this reaction, which is happening like in a batch reactor, you know. So the first thing is that A is our main component here, so everything will kind of be written in terms of A, and this is kind of a molarity of the concentration in that batch reactor. So the disappearance of mole of A, what we call the rate of disappearance for A, will be negative. Now this is what we call elementary reaction, shown here. That's elementary reaction. So the coefficient that you see around the in this case the component A, B, or C, for A is a 2, for B is a 1, and for C is a 1. So be careful with that. Now if it's an elementary reaction, what we are saying is that the rate of mole of A disappearance of the concentration of A as it disappears will be minus K1, because that's basically the rate constant here going in toward that direction, times the concentration of A squared that go that way. Now in this direction coming back is going to be B. This coefficient is not there. Remember, I'm just telling you that there's 2AB, so this reaction going back will be K minus 1 times the concentration of B, and that will produce the 2A. So this is the rate of disappearance for the concentration of A, of that component. Now here is where this 1/2 is become very important. For every mole, if we can talk about that, if every mole that disappear, then B at least 1/2, and that's where it comes. If a mole of A disappear, at least 1/2 of B should be there, right? That's why if you divide by 2 and that 1 divide by 2, say you get the 1/2 here. See, and so basically now toward this direction B is positive, meaning that the rate that you're going to write for B will be 1/2 whatever is about A, and A is here. Check the sign that changed. Now this negative disappear, and whatever was positive here is now negative because it's coming back. It's going back. So that's the only part that you want to be careful here, and that's how you write this expression here. Now B also has a second part to it, which is this one. B will disappear towards C, so the relation between B and C is 1 to 1, so there's nothing to change here, minus whatever is this constant, which is called K catalytic, times the concentration of B toward that direction. So we finish this second reaction. That's how we express the disappearance or the appearance of B. Now finally for C, the rate for C will be equal positive. Whatever mole you disappear of B, it will become eventually C, if we are only considering this reaction here, which is the one that we care, because basically C is formed by B as shown here, and that's it. So now you have what we call the kinetic balance, the 3 reactions that we need in order to study the dynamics of the reaction. The data show here that K1 is 0.1, K minus 1, that's the reaction, the reverse reaction, is 0.02. Now the K catalytic, which is called K2 here, but it's K catalytic here, is 0.001, and these are the original concentration at time 0. Remember, this is kind of a batch reactor. Only A, we only have A, which is 1 mole per liter. B0 and C0, they are both 0. How can we put this together and solve this problem, this dynamic? based on these three reactions. The method that I'm going to be using is called Euler. So this equation will be transformed to a Euler form, and that can be done very easily. So this is what we're going to do. Let's write here parameters. I always start with this. Let's see what are the parameters. And then values, and then units, and basically let's start by K1. K1 is 0.1. I'm not showing the units here, but this constant will have units. So but definitely the main point is that they will be in seconds. They will have seconds as the basis for the time. K1, then I have K minus 1. That's the reverse reaction, is 0.02. And now we have K catalytic, or K2, whatever you want to call it, is 0.001. And the initial concentration, the only one that I care is the initial concentration for A, which in this case will be A0, which is about 1 molar, or mole per liters, and B 0, and in this case C 0. They're both 0. All right, so that's good. Now, before to proceed here, the idea is that I would like to know, based on this value here, what would be a good delta t in order to integrate this, because the integration for this equation will be numeric. So I'm going to be using, as I said, the Euler method, which is a numeric method for integration, but then I need to define what would be a good delta t for this, for the study of this dynamic. We can start with using this equation, and basically what we're going to do is express this equation in terms of delta t, based on the precision that I would like A to be shown. So what would that do is the following. Let's say delta t in this case will be the absolute value, because that's basically what I want. I just want the time. What is the time basis for this? Will be this value here, dA. Let's say that the dA is going to be 0.1. Could be smaller, but that's good. But that's a good start. And let's find out where this will take us. Divided by all this expression here, that will be minus K1. Let's put it like this. I can put it like minus K1, which is this value here. Oops, I'm missing the equal here. There we go. Minus K1, it's right here, times A squared. That's the only A squared that I have, is this one here, the initial concentration. That will be square. Now, I have here plus K minus 1. That would be this one. Obviously, I know that's 0 for the time being, but let's put it as a general, time this, although 0, no problem. So we close that parenthesis, and we close the other parenthesis. So now from here we're gonna get an estimate of what delta t will be into about 1 second. That's good. So basically the time basis for this is I'm gonna run this integration basically at 1 second. I can run it, I can use, like, instead of 1 second, use 0.5 or use a smaller time, but not larger. If I want the precision that I put together here, the precision is about 0.1, and you will understand what that precision means. Now, I'm done here. It's just writing, put it together the table. That's T, that's A, that's B, and that's C. Those are the concentration. How are we gonna do this? Very simple. Let's organize this. Start to look better. There we go. Oops. There we go. So we're gonna start at 0. And the initial concentration for A is 1 molar here. B is 0. C is also 0. Now here we go. For T will be then this value plus this value. Now put a dollar here. And now you drag this, obviously will increase the time 2, 3, 4, 5 seconds, etc., etc. Now, what's the concentration of A here? Well, for that we need the Euler version, the integration of these for my new value of A. Basically, it's just multiplied by delta t everything. The delta t cancel this side, but it stay here on this side. And what's delta A? Delta A is basically the new value of A minus the initial value of A. So if I put this here and express everything based on the new value of A, is the old value of A plus delta t times, open a parenthesis here, and that will be whatever you have here. In this case is minus k1 times a squared. Now the a is not from here, but remember that a is the old one value, so that you pick it from here. That has to be squared according to the equation, plus k minus 1, that's this value here, time b also come from here. Now close the parenthesis. Couple things to fix. Remember, you're gonna drag this down, so b12 will change, but b9 will stay, b2 will also stay, so you have to put $1 to fix that value. b12 will change. Now b3 will stay, and basically you have that done. So as you can see, from the change from 0 to 1 second is 0.9. That was expected, because basically when I start this problem, I started like let's see where we are here. Right here. I started with a 0.1, so the precision was to be about 0.1. So that's good enough for me. I can make it smaller, but that's okay. Now what's B? B depends of all this here. Now, one thing that I could certainly do is copy some part here, which is kind of a repetitive. You see that everything here is this part here, but there's a change on the sign. That's the only thing that I have to be careful. And there's a 1/2 here, so I can definitely copy all this. Maybe better it's just to redo it so everybody understands what I'm doing. So it's basically the old value plus delta t, which is this value, times, careful here. Now I have the 1/2 here. I can put that 1/2 here, 0.5 times that b9 times, careful here, they said k1, that's a positive value, time a squared, which is this value here, oops, minus k minus 1 times b. There we go. Close that parenthesis. Now I think that I need to, that parenthesis will take care, but there's a delta t here that I have to be careful here. Let's see, how can we fix this? That b9, I gotta move it from here, and you will see in a second why. Because it's the 1/2 only take care of this part here, but this part here that has nothing to do with that 1/2. So now with the whole thing has to be multiplied by delta t. So that's why I have to be careful here. Put another parenthesis here, and then keep adding here the other part, which is minus this value here, time b. Close our parenthesis, and now here is the delta t that I need to write down, is this value times that. So I have to be careful with that, how you put this on this Euler version. So now if b9 is the delta t, that will not change, b2 will not change, b3 will not change, whatever is constant will not change, and this one will not change either. So I think we are okay. Let's see, b9, b12, b$3, anything else that need to be changed? It doesn't looks like. Let's see, it looks good. Let's see what happened. All right, so we are increasing b. I mean, a drop, but b is increasing. Look good. Now how about c? Well, c, I need to write this equation in terms of that, and that basically will be k2, so that will be the old c plus delta t times, I'm gonna put the parentheses, so that's not needed, but I want to be sure that you understand whatever is in parentheses, just this expression here. And that would be K2, which is K2 is, in this case, is K catalytic, times B, close parentheses. And now B9 needed is a constant, B4 is a constant. I think that we are okay here, enter. So there's no B, obviously there's not going to be C. Now let's pick this to be sure that everything looks good, that I haven't goofed up anything. It looks good. It makes sense. In fact, it makes sense. 0.1 was the mole chain here, and that 1/2 would be B. So that's basically what's happening here. Good. I think that we got this pretty well done. And anything else that I might need? No, I only need to run this and see whether I miss a $sign or something, because it's gonna get screwy. I see that B is increasing and A is disappearing. Looks good. And C start to increase now that I have a little bit of here. And so it looks like I can still keep going with this. How about if I drop everything together now? Perfect. I think that we got this. We nailed this down. Let's keep going. Keep going. Good. Let's keep it. Let's see. Let's get this to about 1,000, a little bit more, and I can see the concentration. Maybe I'm not sure whether this is going to a steady state value, and so this one. The best way to do that is to do a plot. Let's do a plot and let's find out where we are. And to do a plot, let's copy the whole thing, Control Shift down, and now let's insert that a graph. Insert. And let's insert here, and let's insert that one. Yeah, that will do. And let's see where it is, right there. And let me see something. Okay, that C is increasing. And what's this? That's B. B went to a, from a maximum value, but now it's dropping slowly. And because C is increasing. And how about A? A drop quickly, but pretty much stay at, I don't know, a quasi steady state sort of. And so let's keep running this a little bit more, and let's figure it out. What would that do for us? All right, so let's see. Let's hit this to about, I don't know, 5,000 maybe. This is the nice thing about solving with Euler method. You can set it up very quickly. So I can see, yeah, basically A is fully disappearing, B is pretty much nothing, and everything eventually is becoming C, based on the fact that above an hour already. I mean, I'm hitting for the second hour here. This is the second. So if you make a plot of all that, let's see if I can do that. There we go. Let's see where I stay. Oops, I think that I was about here. Let's grab it completely so I can extend the graph to 5,000 seconds. Let's see where we are. Oops, way too much. More than enough. And let's find out. All right, so that's basically it. I mean, you can see increasing to the maximum value that is going to be hitting about 0.5. Basically, you start with 1 molar of A, and that 1 molar A eventually will become half a mole from B. Then eventually this mole of B will be irreversible converted to C, so eventually whatever concentration you have to B will be eventually will be a concentration of C. And that's basically how this the dynamic looks like. And so I think that I have nothing to say except that this is C, the concentration of C, slowly getting up to the maximum value of around 0.5. Here is the blue is the concentration of A, the orange is the concentration of B that went through a maximum value here somewhere. I can certainly do that and reduce this so you can see it easily. So let's get this to 500 seconds, and you can see that the maximum was somewhere here around 50 seconds and then start to drop after that. And that's basically it. You have the dynamic, very simple, using what? Using the Euler method, basically, for integration of this differential equation. And as you can see it, you don't have to write this in the Euler form, if as long as you understand what this means. Delta A over delta T, that's what they are, the rate of change of A versus time. So you can change this T by a delta and then resolve for the variable of interest, which is in the first here. The solution of A is the solution of this differential equation, and so for B, and so for C, and those are the result. Very straightforward. When you get the kinetics done, then remember this is for a batch reactor. I'm talking about a batch reactor here. All right, a CSTR will be something else. This is a batch reactor, and how you take this reaction in series, just to set them up and do all this dynamic extremely straightforward, as long as you do properly the conversion to Euler method, and number two, that you properly use a delta T. I can use a higher value if I want to, but I will lose precision on the calculation. Let's say, for example, I can put 5 seconds here. Sorry, not 5 seconds directly, but here, instead of be 0.1 here, let's say I want to measure every 0.2. So delta T will change, and the whole thing will change accordingly. But it will stay 1 minus 0.8, that's 0.2, right? Because that's what I put for the calculation of delta T. I can put 0.5, that's the precision that I want on my concentration. So as you can see, this is how it will look like. Less number crunching, but it still look good, so I don't see a big deal. Let's see, let's change something here. Let's get here and let's reset that, and that's basically what we'll say. I mean, the whatever you start with concentration, you can see the orange here, that's the B, but you can see the blue start at 1, but it dropped and eventually it's just gone, and so B is gone as well. So the only thing that remains was basically C, which if you check the end of it, it's just hitting almost pretty much getting to a steady state value of basically 0.5, which is supposed to due to the stoichiometry of the reaction. Well, folks, that's more than enough for this very straightforward example. Have a great day. Bye.